Alright, I'm testing the volume on the stream before I start. I guess it's there. Yep, we've got it. Alright, what I want to do today is just start us in the mindset of uh, friction. Okay, so you have internal forces on this page 368. You move along to the point where you reach the next chapter, and it has a picture of a wheel, but here, let's hit it. Let's try it again. There we go. So it has a wheel, and it's it's friction. So imagine, if you will, I think I can draw on this. Let me see. I kind of, I don't know what's going on here. It's pretty slow. Okay. So imagine, if you will, you have something sitting on the carpet here. The carpet's kind of rough, so here's your carpet. The bottom of this box is pretty rough. So what happens is, if you do a free body diagram and you look really close at this, you'll find that your box has to run across the carpet and go up and down across this. And you've seen that in carpet before, where you would move a object that sat on a carpet a little while and it embedded in there. This is something called dry friction, and through a series of experiments they've determined, and you can do these experiments as well, that dry friction is proportional to the weight of the object. In other words, here, let me go to a fresh page. In other words, if you, now I'm going to have to apologize already. This thing is acting very strange. So if you have a 1 pound piece of furniture, so if this thing weighs, say it's a very light piece of furniture, it doesn't take much to move it across the carpet. But the heavier it is, the harder it is to move. So what you'll notice is this force becomes proportional to the weight. What they'll do is sum the forces and say, well, this is a normal force of the ground pushing back up on the piece of furniture. So they basically go in and do experiments and determine this. Now, I remember years ago going to a museum, a science museum, and they had an interesting display. They had a 2x4 on this 2x4 they had several surfaces here. One of them was carpet, where they had attached carpet to the front of this. You had a block, and then what happened is, and it was attached here, you would pick this thing up until the block slid down. Let's take a particular case like that and see if we can figure something out. Let's say that it just so happened that we had this block. We did that, and we found out that this was 30 degrees when the block started sliding. So if you look at this, it's saying, and this S is for static, that the equation looks like this. And if at if at 30 degrees it starts sliding, what do we have here? Well, let's take a look. First, we have the weight. Mm, let's just say that, well, how should I say this? We'll, just for case in point, we'll call it 10 pounds. 30 degrees, we would have, and I don't know that this is actually 30 degrees. Um, Actually, you know what? Let me try something. I think you can do something like this. Maybe you can't, but yeah, I won't worry about it. Okay. So the question is, which one of these is 30? Which one of the angles is 30? Well, it turns out that since this line right here crosses this line in a perpendicular, and this line right here crosses that line, that this in fact becomes the 30 degree. So you've got a situation where you can easily determine this. So this, which becomes the normal force. So your normal force becomes, it's 10 times cosine of 30. I'm having to write kind of slower than normal because for some reason it's having trouble keeping up. And then the force pushing it down the plane, I guess I'll say P, pushing it. There's not a person back here pushing it now. It's its own weight pushing it. It's 10 times sine of 30 degrees. And so now at 30 degrees, it starts sliding. Let's say it like this. At 30 degrees, at 29.999, it didn't slide. At 30, it started to. So there's this concept where you're caught in between. So now we've got an interesting circumstance here. We've got our F. Here, let me see if I can kind of, having to draw slow. This. So now instead of writing it there, because I have a clustered kind of, I'll write it here. Sine of 30 equals 2. Now this is this term. The mu, whatever that coefficient is, which actually becomes coefficient of friction. And now I'm like looking at the n over here. Now the first thing you realize is as long as you could pick this thing up, as long as you could put enough force here to pick this up, this 10 pounds doesn't matter. Doesn't matter if it's 10 pounds, 50 pounds, as long as you can pick it up. If it's too heavy and you can't pick it up to reach its 30 degrees, then, hey, so what? But it turns out that you end up, well, you have a sine here and you slip a cosine under it. And so, instead of just carrying this as 30, I'm just going to say that. Because maybe it isn't 30. Maybe it's like 15. So just out of curiosity, let's think about this. Okay, first, if you have it flat, there isn't even going to be a force trying to move it down the plane. So let's take a look and plot, because I do have from the last class, okay, let's do a clear. And what I'm going to do is I can go from an angle equaling to, say, 0.1 up to 90 degrees. Now, 90 and 0 are kind of ridiculous. Now, if you don't want the output to come out, you can put a semicolon there, and you don't get an output. Now, I said A, but you know what? Well, I can leave it as A. And then, well, but I want to plot this. So what I'm going to do is I'm going to go out and say the angle is x. And then I'm going to say y is equal to the tangent in degrees of x. And I don't want the output to show up. And now I just want to plot x versus y and give it a second. Oh, it shows in a very tiny window. Oh my, does it take forever? Uh-oh. Am I not seeing something? Oh gosh. Okay. So, you know what? Maybe going to 90 is not a good idea. How about we go to, instead of to 90, because 90 is going to run you off to infinity. How about we go to, reasonably 55? Hopefully that won't take as long. Oh gosh. Oh. Yeah, yeah. I went to 55, but I've got to do the tangent. Now I got to do the plots. Okay, so if you see this thing, what you'll notice is the coefficient of friction. Let's see what kind of tools I can do. Edit. Yeah, it's not a very good picture, but at 10 degrees, okay, I don't know if you can see this, but that's about 0.5. This is about 1, which runs you out here to like, I can't tell, maybe 45 degrees. 50 degrees runs you maybe at 1.2 or so. So the numbers, and legitimately, you could like take your surface and glue the block on there and then turn it straight vertical. And yeah, if it's turning straight vertical and there's a force down and your normal is equal to 0, so your normal would equal to 0, your force would be equaling to 10 pounds or so, or whatever it is. And then you would say, well, F is equal to mu n. Hey, wait a minute, if it's turned totally vertical, then yeah, mu is equal to infinity. Well, so this is if you glued the block onto the board. Okay, so, but that's not going to happen. So the question would be, is what would different substances give? Well, let's see if I can find the book again. I think, oh, here we go. So here's some of your typical coefficients of friction. Now, he starts making this little comment right around here, but I don't know if in fact there's a complete description of that. But in any case, here's some typical values. Okay, so if you had something like metal on ice, it would pretty much, you'd lift that piece of wood, and let's say if it was 0.05, what angle would it release at? So if you came back and you said this was 0.05, what angle does that, if you lifted it, what angle were you having to lift this at before the block of ice slid down the piece of metal? Well, if you looked at it and you did a tangent degree of 0.05, you'd realize it was around 2 degrees, maybe 3 degrees, it starts sliding. Now, if you go back here and let's say, wow, that's a pretty wide range right there. Let's say it was around 0.5, halfway in between there. So what angle would it take if this were mu point equal to 0.5? What angle would that be? And it's pretty simple. You just go in, you take the arc tangent of the coefficient of friction, 26 degrees. So at about 26 degrees, you would break the surface there and it would start coming down. So as I remember in this exhibit, they had some boards covered with carpet, they had regular wood, and they had an actual glued on Teflon sheet. And then the blocks had things glued on them. So the blocks weren't very big. They were maybe 6 inches by 6 by 6. And this, I think, was a 2 by 6 with a regular door hinge connected to a table. And as I looked at that, it wasn't glittery and glamoury, so the kids weren't actually running around playing on it. There were a few, but they also had an exhibit where you would go in and have a race. So they would have this thing that was maybe 6 foot tall. You would step up on a stool and drop your object, and across here there were like several tracks. One track actually had Teflon, and the others had something else. One was regular house paint. And as the blocks slid down the plane, the kids were having races. So that made it fun. But this little part here where you could actually get data out of it was pretty boring. I don't know if that display is even there anymore. Let me see, just out of curiosity. The computer is really bogged down. I'm not sure. I don't know if they would have a picture of their... Wow, this thing is slow. Yeah, this is all going to be events and exhibits. Let's see what they've got. Yeah, there's a permanent galleries. Let's see what's in there. Okay, I'll push the button. Okay. Wow. Let me just sort of see. I doubt these exhibits are there. Anyway, they were there at one time, and the computer is operating very, very slow right now. So in fact, you can easily determine this. Now, what's interesting is if you stare at these two pages, okay, so I related the object to sliding down the plane. And I related the angle, and I didn't call it this angle. I think I called it theta. And looked at this. But there's another way to look at it, and that is this way. Okay, so when you have a weight, then the normal force, some of the forces in the y give you the same. To actually move it, now here's the thing, P can be smaller than this frictional force, but here's what I mean. Maybe it's better just to keep going over here. Let's see. Let's get back to... Okay, so let's look at kind of the way he was describing it. And let's put numbers with this so it makes sense here. So let's say this thing is 100 pounds. and it's 2 foot wide, and it's 2 foot wide here. Now, what happens to you is you start pushing it or pulling it, and let's just say you decide to pull it right here. So it's very important where you pull it. So here's my pulling force. Now, if I come in here and look at this, I find something pretty interesting. First of all, I have a normal force. Okay, when I start pulling it with a P, let's say the mu here, just to make my life easy, is going to be 0.5. So here's your normal. It's going to equal to 100. So does this automatically make the friction force equal to 0.5 times 100 or 50? What would happen if I pull it with 25 pounds? If I pulled it with 25 pounds and I sum the forces in the x equal mass times acceleration, and this were truly 50 pounds and this were 25, the block, by pulling it to the right, would accelerate to the left. So that's not possible. So what is this friction force? And how does this work? Okay, so friction force is equal to the maximum force the ground can put on the block to resist. I'm sorry, I'm having to movement. In this case, it's 50 pounds. So if I pull it with 25 here, guess what? This is going to be 25. There is going to be no acceleration. Now, if I moved it to 35, this is 35. If I moved it to 40, this is 40. If I move it to 50, this is 50. If I move it anything greater than 50, it starts breaking loose, and suddenly it becomes, after that point, it becomes a dynamics problem. Now, you got another issue. The other issue is this. If I went in right now and I sum the moments about, I'll call this point E. So let's sum the moments about point E. And in my standard method, I'll make that. Now, it's not supposed to be rotating, so it's going to be 0. What you'll see is I'll get this 100, and I'll get this P. Now, this distance is 2, and this distance is 1. So what happens here is kind of interesting. Let's do this. Let's now sum the moments about this location. Since that was E, I guess I'll call this, I better not use F. How about G? Now, if I sum the moments about G here, I get a very strange circumstance. Okay? This force, and this force in the current drawing produce no moment, which means this is producing a moment about G. So what does that mean? Well, you know what that means? That means that naturally what happens is this point becomes moving to the right. Hello? Hello? I don't know what's going on here. So this may make G right there. Now, unfortunately, my friction force is kind of in the way. Now, I've kind of goofed up in putting my values here. So what I'm going to do is I'm going to just go ahead and say this is 0.6. So this means that the maximum force that this can resist will be 60 pounds. And you'll see why I'm doing that in a second. So the question might be asked, how far is this from the edge? And I'll call it a little e. Because it's possible that the block could tip over. And there are several circumstances here. Doesn't slide, no slide. Or it could tip. Or it could tip and slide at the same time. So let's go in, and since I've got the drawing here, since I have this, I'm going to change this around and sum the moments about the G right here. And I'm going to take the E off for right now. So if I sum the moments about that point G, the friction force, the actual friction force, which I'll go ahead and call it A, FA for actual friction, it's not going to produce a moment about G. This one will, and it will be this moment arm. And this is point G here, so it's going to be this moment arm. So in this case, I'm going to have 100 times, guess what? This distance from here to here is 1. So 1 minus E. That's going to be the moment produced by this force right here. Oh, shoot, here. And then I've got P, which is producing a moment this way about G. P times, in this case, 2. So let me rearrange this. This has to all be 0. So let me rearrange this as best as I can. 100 minus 100 E minus 2P. This has to be 0. So let's stare at this for a minute, kind of keep track of it. Then we have another equation that says, hey, this thing can reach up to 60 pounds. What would happen if, in fact, I pulled it all the way up to and including 60 pounds? So if I pulled it all the way up to 60 pounds, in other words, if it was 60, that means this would resist it with 60, which means that's the maximum it can resist. So that means I could put in 60 here. So minus 2 times 60 becomes 120. Oops, 120. And now I've got this other 100. So it gives me minus 20. So now my equation becomes minus 100, and I'm trying to draw slow, minus 20 equals to 0. So that means I move the minus 20 over, it becomes plus, and I end up with the E being minus 20 over 100, or equaling to minus, what happened there? 0.2. Meaning that in order for this to be balanced, I'm going to move it, but I'm going to also move it back. This point G has to be relocated. Oh, shoot. Okay, try it again. This point G has to move over here. And that's not possible. It can't resist that. So the crazy thing's not going to work. So I've got to be able to keep this, trying to reline it back up, back over here. So in other words, if this block has the coefficient of friction too high, meaning it's sticking to the ground too much, pulling it near the top, it's going to tip over. Now, if I were to reduce this to say, now, I'll tell you what, I'm going to do this. I'm going to change the ink. I'm going to say, now I'm going to reduce this to 0.4. So if I reduce that to 0.4, what happens? Well, this thing gets reduced to 40 pounds. Okay, so that means it'll start sliding at 40, which means I can go over here and slip this in at 40. So my equation for mu equal to 0.4 becomes 100 minus 100 E minus 40 pounds times 2 becomes 80. So now I get 100 minus 80 minus 100 E, and this all was equal to 0, which means that gives me a 20, and I move it over to the other side. Minus 100 E is equal to minus 20, means that E is equal to plus 0.2, meaning, if it becomes a little less, if it's a little bit slippery on the bottom, then I can pull at the top, and it'll actually slide across the carpet or whatever. So the key is it could tip if, in fact, to keep equilibrium, meaning that this force has to move outside or off of the object. If that's the case, it's going to tip. And so in this case, the 0.6 is such that it's too much friction. And if you pull it up too high, it's going to tip. So he goes through this down here. Okay, so this is another thing that happens. Okay, so let's take a look at this, what he's saying in this drawing here. Now, I'm having to draw slow, so Monday Monday will be in the classroom. So what happens is, let's say the case we just did, the static friction was, say, 60 pounds. Or now let's take the 40 because that one would actually work. So you pull on it with 10 pounds, and the resisting force is 10 pounds. You move up here to 30, it's 30. You move up to 40, it becomes 40. Anything greater than that, it starts having motion, and that's a class called dynamics. And so at that point, sum of the forces in the x direction is not equal 0, but in fact, it equals to the mass times the acceleration. And so at that particular point, you're moving into a dynamics. And what happens is this is really what happens, and you've experienced it as well, where you start pulling something, and once it breaks free, it moves pretty quick. So once it breaks free, it's moving, and it's actually usually a little easier to keep it moving, this is meaning dynamic friction, than if you stopped and it settled back into the carpet a little bit. This is what would be required to break it free. And so sometimes this distance is fairly small. For carpet, I talk about carpet because if it's like a shag carpet and it drops down a lot because of the furniture's weight, then yeah, that's quite a bit of difference. Okay, so then, okay, again, very annoying, the movement here. So I'm going to go to the other systems next week. So here you've got a point where a ladder, or this is a weird thing. Maybe a ladder without a center support, which I don't know why you would have that. But in any case, a ladder in which you had a frictional component based on that, and a frictional component here based on that one. And it's possible that there could be two different coefficient of frictions there. This is a case where there is a different coefficient. I mean, this maybe is the ground dirt, and maybe this is a smooth wall, but that wouldn't make sense because they've got it listed in opposite. But anyway, so all you're doing is breaking apart your free body diagram and working it out from there. Oh boy, it's not moving. So here's a particular problem. Somebody just pushes the box, some sort of crate. Your first thing, you do a free body diagram. You don't really know exactly where this is going to end up. It's got to move. If you're going to have some sort of force, it's going to, based upon what's happening, it's going to have to move off of this center directly under that weight. In this case, he moves it to the right and says it's going to be x to the right of this O. And he's going to try to find that x probably. Maybe he doesn't want to find it. I don't know. I'm wrong. He does want to find it. So obviously you've got three sets of equations. This one is probably the most boring one. I tend to do it first. So you've got this force is offset by, of course, this force and the component of that force going down. Then the x, you have your frictional force, which you're not sure what it's listed yet. And notice right here, he does not put in mu times the normal. He has to logically argue things in order to relate, he calls this NC, relates the friction force to the normal. But what happens is you get the x component here and the x component here, and they offset each other. So he waits till he gets done, and and then he sums the moments. This is a standard. There are two places you can sum the moment that are kind of handy. One is this one, because you eliminate things, but if you're trying to find the NC or bring that into the equation, which right here and right there, then it's best to sum it right there. I'm sorry, that's Newton. Here's your NC. This thing is really slow. There's your NC. So if you're summing the moments by x, that moment arm times the NC will sit in there as the moment. Then you've got to take care of this one, and you got to take care of the portion of the load that goes. Okay, so in this particular case, since the point of application of the load is right here, you would place the component right here, and then you would place the component right here. This one, the moment arm would be this distance. This one, the moment arm would be this distance. He solves all those three equations, gets the F, the NC, and that. Then he says, okay, got all that. Since x is negative, it indicates that the resultant force acts slightly to the left of the crate center, meaning he didn't have to actually know whether it was to the right or left. You just have to assume it and then figure it out. No tipping will occur since x is less than that 0.4. Why? Because this is the distance here. The NC doesn't move out over here to keep to keep the um, to keep equilibrium here. If it had to move too far over to the left where it was way past that 0.4, then you got a problem. Also, he says, wait a minute, give me a second. Man, this is slow. Also, the maximum friction force which can be developed at the surface is that which is 70, which happens to be, and thank goodness for that, it happens to be slightly less. I'm sorry. This force happens to be slightly less than the frictional force that it can take. So it says the crate will not slip, although it's close to doing so. So this is a pretty good problem. It's not mathematically complex, but this part is very important because this gives you the logic of what's happening. And so I think we'll classify this as being our coverage of the friction, and I'll maybe work a problem. I don't know if I'm going to work a problem Monday or if I'm going to go back and do some beams on Monday. I may go backwards and do beams on Monday. But friction is a fairly simple thing, so I'm going to call it quits for the time being. And I have to apologize for